Okay. All right, let's continue our discussion of segmentation. So just a brief recap. What is segmentation? Normally, we have a grayscale image typically. In our eyes, especially if we have pretty good resolution, see multiple phases in that image. And if you're talking about an X-ray image, phase in the image is identified by similar grayscale values typically. And similar grayscale values in X-ray image means similar density. Now, we would like those to also mean similar material or same material, but that's not always the case, and that depends on which type of imaging you use. So either way, whatever our eyes think they see in the image, we would like to group and simplify. So in this particular case, I have air, and my mouse is not moving. Let's duplicate the slideshow. So in this particular case, I have air, I have glass beads, and I have water. Okay. And I would like to separate these in 3 groups. So if I'm coming in and saying I want 3 groups out of this, that also means that I know how many there are. So keep that in the back of your mind. You don't always know how many there are. So one objective would be also, well, identify how many phases there are, okay, before you actually do proceed with an algorithm to separate them. So what we can rely on in any image is really image values. I can, in this 2D case, refer to them as I of xy, and gradient of these image values that gives me another scalar, or in general gradient of the image, which is a vector, right? So this is square of the gradient, of course. So the gradient, where gradient has large values, I have large changes, so that can give me edges of the phase, especially if I don't have any noise issues in the image. So basic idea of segmentation is to look at my image and basically divide it in groups. If I look at a histogram, which is statistical representation of all of the values in my image, that idea translates to being able to separate peaks. And that's sometimes possible, sometimes not so possible. So I also might need to do quite a bit of filtering of the image to actually get there. Okay. So if I don't, so this is an example of where I have a very poor distinguishing of the phases in this given image. So you can see that the histogram is not very well differentiated. Okay. All right. So most of the time, this basically thresholding or finding a threshold to separate these two is the simplest thing to do. In this case, it's actually a no-no until you actually process your image further. But it's nevertheless some of the most common. So question still remains, well, what should this threshold T be? And there are different methods to find it. It's subjective. So my joke is that before a coffee in the morning and after coffee in the morning, I will decide the two different thresholds are good for whatever application I have. So there is a little bit of variability. As long as that variability is not large in terms of the number of voxels and what do they volumetrically mean in the image. So if you're affecting only 0.1% voxels in your entire image, well, that's not a huge deal, right? So there is certain element of uncertainty that we can deal with. There are methods that will try to separate the peaks better, but they're working in a statistical sense, and locally I still need to evaluate whether that given method works for me or not. So there is a danger in just trying to work with things on the entire image. Methods should technically be locally adapted. All right. So we had an example. We had a simple thresholding exercise, and we imported our beads data. Those two peaks are well separated. Even if I have locally small issues in the image, they're kind of always there. And they are going to result in segmentation errors. So we cannot necessarily be completely error-free. So we did the thresholding exercise. We see that these beads actually have beads themselves have some issues, and they're not the most perfect beads. So that is fine. That is reflected in the image and its reality. It's these movement issues, such as this one, that are more problematic. So there was probably some relative movement of the bead that has resulted in this problem here. Okay? So we have done that quantification issues. We have to understand that we are relying on grayscale values. So in this case, individual grayscale values, this is a photograph. It's not an X-ray anymore. And it's not these grayscales are not a function of density. There's also reflection and transparency that play a role. So even though this is as clear of a photograph as one could imagine, there's a problem here because if I use grayscales to identify this phase, I have any grayscale possible actually here within what's my oil phase. Okay, this water phase is a little more even because it's transparent, but this one is not, and that's going to cause an issue in trying to identify this phase. This is what your OTSU or blind application of OTSU method would do if you segmented this image. So this you just should be no business segmenting, not this way anyway, right? So that we have to be careful about that. So I'm going to introduce multiple algorithms today, actually, and specifically statistical region merging. So we're going to get to it as we go. How do I evaluate segmentation? Well, technically, to evaluate how something works, I need to have a known system. And that can happen two ways. I can start with a test, throw in some noise, and then see how does my method do. Or I can image something where I have some other external corroboration of what's happening. So for instance, if I was imaging a capillary tube and capillary interface between two phases, liquid phases in a capillary, then I know what my outside pressure is and I can physically solve for the problem. So if I measure the curvature from the image, then it should basically when scaled with the interfacial tension, I should get the capillary pressure that I measure externally in the system. Right? So I have to have some way of measuring, or I should really spend a lot of money purchasing pretty nearly perfect beads and then make sure that I get perfectly spherical creatures of the same radius when I actually image it. Okay? So there are multiple software. Basically, the segmentation in terms of thresholding is implemented everywhere. It's the more intense or better algorithms that are more problematic to find. And we're going to try some of them in ImageJ. MATLAB is another place where there could be some widely applicable images. At the end of the day, we will also have to filter our binary result, our image that we get from segmentation, just like any other image, simply because segmentation as a process will introduce errors. Okay? So that's almost a necessity. So you can either do the speckle or a median filter. That's our friend from filtering grayscale images. You might need to apply it again for a smoother result. Okay? One thing that is dangerous is erosion and dilation. We're going to mention them in our next lecture. So I'm gonna postpone the discussion about erosion and dilation for then, because those can affect a large portion of voxels. So in terms of fraction. And these operations, what do I do with binary images, will be a separate topic. So in summary, we start with the tomographic image. This is a very bad example, but basically shows a danger of using too simplistic, not filtering enough, and using too simplistic of a segmentation method on it. You get a very noisy result. In terms of a fraction or porosity, you actually might be just fine if you're evaluating fraction of anything in this, because that's sort of a volumetric measure. But anything that depends on smoothness of this, like let's say that flow or reactive flow or any other simulation that depends on these interfaces, you won't be able to discretize this image and you won't be able to do simulation on it. This is a way better, this is something to shoot for in terms of smoothness of the of the boundaries. Okay, so we want the result to ultimately be this, so we want to avoid noise as much as possible, and that's called quality segmentation. Now I'm gonna switch to an example again, and then we're gonna do final comments as well. So let's go to our friend not so clean sandstone. It's actually pretty good. So our little sandstone Benheimer sandstone image. It's a raw volumetric image. And play with image types. Your possibilities are 8-bit, 16-bit, 16-bit, and 16-bit unsigned and signed, and little endian and big endian until you import it. So import it, and then we're going to actually see the effect, so the point of this exercise, and we're going to actually do multiple algorithms on this, but we're going to start with our simple segmentation. But before I segment, I will do different ways of filtering this image just to see what is the difference. So before you, well, let's everybody open the image.
This time is 16-bit?
Yes.
Unsigned?
Little endian.
700 divided by 300?
That's what actually says in the NX and Y and Z. That part is recorded. Actually, this is unsigned binary short, which is 16-bit. So has everybody opened it? You ready to comment? So if I just do my binary segmentation, so segmentation often works by segmenting things into two phases, then my Otsu method, for instance, or I will either set a threshold or Otsu method will do it for me. Okay? That's great, but how many phases do we actually see? 3. So there is the main grays. I need to apparently duplicate slideshow. Okay. To show. There we go. My mouse has shut up. So there is a solid phase, there is a pore, and there's something here in between. This is likely clay. Okay. This might be actually a problem of some sort of movement, or otherwise I typically can have issues near the boundaries of 2 phases. So I'm not certain that this is clay. Maybe it is, maybe it's not. I don't have image that is clear enough to know. But it's also some sort of an intermediate phase. Okay. And then I have these cracks. Cracks are inherently pore space in between 2 solids, but they're so thin that they're actually going to show up as this intermediate phase. Okay? So we have to be careful about that. So here's what assignment is going to be. And let me walk you through the assignment and the comparison that we're going to do. So I'd like you to do a very nice comparison that compares different things. So I'm going to ask you just to do basic visualization and report and save slice 95 and see and report orthogonal views of this sample just to recall how we do that. And what is the histogram of this? Okay. So that's first, like image coming in, original image, right? So this is original.
So when you say report save slice 95, it's just like
so
slice 95 and just taking a snapshot.
Take a snapshot, and what we want to do is compare this slice 95 across different things that we're doing. Okay? So kind of have a table in mind that compares the two, or you can put this into a PowerPoint or however you see fit. But then we will proceed and segment this. Okay, and again, save result for the slice 95 just to visually see what does this Otsu method do in terms of choosing threshold. And I'd like you to then spend some time looking at, how did this contact, this type of contact, get resolved? And we can probably in slice 95 find another contact. What is the overall assessment like of the quality? And calculate porosity. So let's do that first. And then what we're going to do is basically use 3 different filters and filter the same image and do the same, right? So for this filtered images, we're going to compare histograms with the original. Okay. And also how this slice looks like. So both visually how slice looks like and general statistics on the image. Okay?
And you add these filters before segmentation or after?
Before segmentation. And then do segmentation and see how does the ultimately you're after porosity, right? So it's one number. And see how you affect, and is porosity affected at all. But at all times try to see where is this intermediate phase in all of them? Did they all have the same decision for the intermediate phase? Maybe, maybe not. And I gave an approximate position of that clay that is neither solid nor void, but you are segmenting into solid and void. And you can also play, so I want you to play with assessing the differences. If somebody is asking you, what is the difference between 2 segmentation methods? You have to have various ways to compare. And this is an exercise in doing that. It's not necessarily easy. A lot of people skip it altogether or don't report in papers. I'm laughing, but I'm not laughing. That's pretty common. Because nobody really wants to spend time segmenting and evaluating segmentation too much. They move on to whatever it is that they want to be doing, right? But you often want to convince yourself that segmentation that you have is working for you. And here I'm giving 4 comparisons, in this case, altogether, this image is relatively clean. Okay? It could look Let me see if I still have it in downloads. Just to briefly give you an idea, it could look pretty bad. And this is coming your way in some shape or form. It could look like this, okay? You actually see a pretty high resolution email here. High resolution image that I apparently don't know how to operate in image viewer. There we go. So you can see pretty high resolution image, but there is a whole lot, because of that high resolution, there's a whole lot of X-ray imaging issues. So it's hard to avoid movement. You don't have enough statistics to get clear reconstruction. So you see pretty high resolution interfaces, however, it comes at the expense of the overall quality of the image. Our eyes see very clear, these were glass beads and 2 phases, right? Our eyes see it clearly, but getting beyond these to segment this in a quality way is a problem, okay? So then filtering makes all the difference. In this little example, not so much, so it's going to be relatively mild, but nevertheless, it's a good starting point for an exercise, okay? So again, filtering and how you filter this makes all the difference in how you're going to segment it. All right, let's get back to this image. So again, start record. So in all cases, record slice, take a snapshot, histogram, okay, and then segment and calculate porosity. And save the segmentation result so that you can quickly load it up if you need to redo something. So save all of these. Save histogram as a list if necessary and as a little image. Okay? So I'm going to write it over there just as a little clearer because I'll be doing things so that we can easily. So slice 95, tomographic, okay. Then histogram. So save image of it, image and list that you can easily refer to and compare later if necessary. Then filter, save output as filtered, give it a name, okay? So volumetric, save, and then histogram, save, slice, volumetric is slice 95, and histogram also save as image and list. And then segment this segment and save this volumetric part. Okay? So we have all these stages and you can quickly save volume as well as slice 95.
So when you say save volume, it means the entire file?
Yes. So you can quickly pull it out if you need it to compare anything. So you don't have to, you know how to redo it. It's not a big deal. But eventually you're going to forget something in this sequence. So just as you go, save. So you can easily reopen it and just calculate what you need. Yes? Yes. And also, if ever in doubt, do that macro record. So in the process, you have the steps of what you've been doing. So I also want you to develop a habit of recording, because it's very easy to go, and it takes a moment. Like I started playing with this image that I just showed you. So I started playing on Saturday night. What else to do on Saturday night? So I was like moving around and I forgot to record what I was doing. Whoops, right? And then it's like, yes, I know mentally there, but you gotta then suddenly spend half an hour redoing of things that you should have been saying. Because you get carried away. And, woo, is that one, yeah, filtering is a challenge. Yes? And this is going to be a reported assignment. So I'm going to walk through the basic things with you. One of the filters. So I have snip and sketch. I'm actually going to replace with my files with modify. So this is my segmented image. Save as. I put UBC as outside binary character or 8-bit. So we can now see that this crack has been preserved fine. This here is that clay. Some of it is pore space, most of it is actually solid phase. Okay? And in order to get the porosity, we can look at the count. We need count of zeros for porosity. That's black. So this divided by 200 cube. Okay. So I saved all of the things in the way. So now the same thing, just for filtered. So I'm going to save this on a side. Did I save it? Yes, I did. And we can save this to sit on a side. Okay. Now I will open this. In my data. So let's do median filter. There's process filters. There's 3D filter here. Let's do 2 by 2 by 2. So now I'm going to immediately save this. As raw. And I have put things in the wrong file, but I'm going to move them in a moment. So it's not a read, no. Filtered, filter, so it's not original, but it's filter, median, 3D, 2 by 2 by 2. Histogram. and then segment. So So I can see, for better or worse, much smoother. You see the surface here? That can create a great deal of difference in terms of if you wanted to simulate on this image. Small stuff kills simulation. Just it's noise. And you can see this clay area here. Again, for the most part, it's solid. Again, for better or worse, depending on what you want to do. That might or might not be a good choice. And then it's a little hard to tell whether this threshold, given it's, of course I have, this is why it's good that I saved, so I can call it and compare neck to neck what is the segmentation doing here and whether it's making a correct choice. And often it's a little hard to evaluate, but you need to basically look at the image directly. So let me import it again. Import. Oh. Filtered one. 2. Oh, it has that 2 by 2 by 2 filter. So it's trying to be smart and thinks that the image is 2 by 2 by 2. Whoa! I have done something. Import. It's twice larger than my, oh, this is segmenting, that's fine. Okay, let's try again. But filter, the image should still be the same 16-bit unsigned, right? So maybe I saved something else by mistake. I mean, this is the mix-up you get with Indianness. Let's try Big Indian, but I'm not sure. So then this is opening, we're saving. Save as raw data, all of this. I would assume that it would go with the same. It doesn't, so this save as routine is not telling me what I thought that I saved it in the original, but this is an interesting, okay, open. Let's get the original. Now that's segmented. Let's do median filter. Still 16-bit, 15 megabytes. I'm guessing the following. My machine is big Indian. Doesn't matter what I add at the end. That's just my naming. If my machine, so this save as is not saving as whatever we imported. It doesn't know about that. If I tell it to save as 16-bit, it's going to do it in the Indianness of this machine. Yeah. So let's test it. I'm just going to 3. Median. 3D. 2 by 2 by 2. Yep. The big Indian. For me. For you, something else. Good idea to put that in the name of the machine as well. Or just go with volumetric TIFF. That could save some trouble. Okay. Yes? Go with volumetric TIFF if you want to just all of this to save it, then you can open it. Let me save as TIFF. Let's just go with that. TIFF. I can then use open, I believe. Is this a TIFF file? No. Let's try this once again. Save as. I'm going to do test TIFF. Maybe I still need to do import. Yeah. So still need to do import, but I can just click on it. It does have to know it's a volumetric TIFF, not just a regular TIFF. You could just throw on image J and it's going to open it. All right. walk through the end of this median 3D just to compare the porosity you get. I'm going to stand back because I see you're all sitting looking at what I'm doing. Yeah, in porosity, it's not a huge deal, right? Right. So it's like 18, 19%. Up plus minus 1%, it's not a huge deal. Where it really starts matter, if you actually need to decide to do something with clay or it's a sizable issue, a sizable amount of clay, then this segmentation into two phases will not be a satisfactory matter anymore. And again, as long as you smooth it out a little, that's good for anything that follows in terms of simulation later. But we need to get to the manipulation to be able to. So everybody please finish at least like median 3D. And then the rest I'll ask you to go through the tedious process of documenting. And I'm doing that on purpose. Can you do image calculator to find pointwise differences? Let me segment this. So I have this one, and I'm going to segment this one. So I have two of them, right? Do image calculator. And apparently the best. So you can say, what is your first one? Segmented. And you can do the second one. I think that's the one. You can do all kinds of things here. You can do add, you can do subtract. You can do math. And just write down on a piece of paper what's the significance you're looking for. So if both of these images have 1, then my result will be 0. So where they match, if I subtract them, my result will be 0, right? Where they don't match, I'm going to get either plus minus 1. So you can work with that. There's another thing to do, and that is exclusive OR. So there's OR. 1 or 0 is 1. 0 or 1 is 1. 1 or 1 is 1. So that's not helpful because if you have a match, 1 or 1 is the same as they have slight differences. Okay? Exclusive OR will give you 1 only if one of them is 1. And so exclusive OR will give you 1 precisely where the differences are. Let's try. And you can see where the differences are. Around the edges, mostly. And within some of those clays. Almost a fun image. And that's the smoothness around the edges that makes a whole difference. So this to me is very revealing in terms of what the differences are. And that's of course where most of the filtering is as well. Okay? So exclusive OR is very helpful for comparing binary images. Can we move on? Everybody got this parts? And you can also count what the difference is, right? So this gives you, you can do the fraction when you do histogram of this and get the number of them. You can see in how many voxels there is a difference, or you can just compare porosities. Similar example. Okay. Now let's actually do something. So there's this subtract. You can again do subtract, or you can do, I'm gonna say subtract or XOR. All right. Now let's do exercise, and the first exercise, Let's do statistical region merging, the first exercise, and then I'm gonna go back to this bad elimination example. Or I have 10, 15 minutes. Let's do bad elimination. I think I need to throw in or share this rice image. I will quickly do that. So do you know where the you downloaded segmentation exercise? I'm gonna PNG. No, I need to move it to that folder. No. So it will show up there in a second. Do you see rice? Okay, open it. I was doing it quickly before the class and I didn't know whether I did it correctly, so I was like, let me redo it. Sometimes when I close my laptop too quickly. So open. So if you downloaded everything, you'll probably have to go there again. So this is a problem with bad illumination. We can clearly see differences, but this is rice. Actual rice, as in food. However, because of the differences in illumination, background here and background here are two different levels of gray. And for our identification, I need the same level of gray everywhere in order to do that. So if you try to do regular segmentation, I actually borrowed this. There's MATLAB top hat filter example. So if you, excuse me, if you, so I think I shared it as rice.png, so I'm gonna. So if you do a histogram of this, test it. So I'm gonna sit back now because if I.
So we have to import this on
No, just open. That's just a single slice of anything in a standard in a format that has like PNG, TIFF, JPEG can just be opened because that format has all of the information necessary. So even though you see kind of a clear image, histogram doesn't agree. So there are some noise issues, and apparently there are 3 phases here. Who knew? Or even more, right? I see multiple peaks. And yet I imaged only rice. Okay? This is not your rock that has issues. This is just rice. Rice is relatively simple. But imaging can have its own. So if you just do threshold, default, Otsu, you name it, there's no threshold you can actually find to. This is just a default choice. You're going to get something like this. So rice is identified pretty well, but then you have a whole lot of noise issues here in the background. So to convert to, so by default it will save this color. Convert to in type, image type. So it says RGB, image type, 8-bit color. Here we go. And then it's 8-bit. Yes? Otherwise, RGB has 3 images in there. So you would have to segment all 3. And the algorithm needs to know about it. And a lot of algorithms don't work with 3. Okay. So now you can slide this up and down. You can use the slider to check yourself and convince yourself. Analyze.
Basically convert it to as an 8-bit type image, then when I go to threshold, it basically does not make sense.
Let's see. Analyze histogram. Oh, wow. This is conversion, everybody. Huh. There's a format. And don't save. Let's do this. What was it called in the original slice? Bad. No. I'm looking on this. So I need to look for something happened in the conversion. So this is also danger of converting in between different. Here's my search. Uneven illumination. Here we go. Copy. Hello. That's all right. It's here. Look for rice uneven illumination TIFF. And maybe this one I need to. Did it show up? in the folder? So I can monitor. I didn't show up. Let me try to log in. If I directly upload. Oh, it shows up now. Let's try this again. Yep. So again, as you slide this, you have too low of a threshold, you're going to have issues in the identity. So this is too low of a threshold. Rice is fine, but then you get a whole lot of extra other parts of the background that you don't need. And you have too high of a threshold, then you identify well the rice at the top of the image, but not so well in the bottom. And this is classical problem when you have uneven grayscale values. In this particular case, if you just normalize local contrast, there's a plugin that does that, and it works nicely on this image. Doesn't always, but here it does. So image process, local contrast. I think I went with default. Oh, yeah, I normalized the contrast on the histogram. Click on the rice image. Don't save. And now when I do histogram, now that's better, right? And now if I segment, I'm going to get a pretty good image. Because I had only 2 phases here, really, and the local contrast was still pretty good in both parts of the image. This worked nicely. And then I can do segmentation, and I'm good. So again, there was still plenty of contrast locally. And this works. I'm gonna just briefly introduce the next exercise that we will continue with next time. So next time we will deal with a little more difficult issues. So we will actually open this Benheim sandstone. That you can actually do that right now, since you probably have it open. And we're going to introduce the method itself, but this method doesn't necessarily assume how many phases you have. It's going to try to merge things locally. Let's see. So if I open again my friend or import my friend sandstone, not binary, but this one. Up. What did I press? Raw. Pressed image sequence by. Huh? And if you just search for statistical region merging, yeah. Oh, convert to 8-bit first, image type. So this will try to statistically kind of start locally, merge and group different pixels and voxels. And it doesn't know how many phases there are. But in this particular case, especially with cleaner images, I'm going to start with 25. I don't know how many there are. And see what I get.
So when we say Q is equals to 25,
It's just like how many phases you think you might have. So you need to start. There's no clear Q that will always work. Remember that about any images. Nothing ever works always. But you should pick a Q that is larger than what you need. And I'm being very safe here. I need 3, right? I have clay or intermediate, and I have these 2 other. And I'm going to let this work in 3D. And then I'm going to get these things that are merged. And so now it looks much smoother, as you see. But actually, I do have these gray levels. And to see actually what I got, I will histogram it. I didn't get it precisely 25. That was initial guess. But I got 3 groups. 3 clear groups. Now I can segment this into 1. All of these, however many, there is 4 here or so, into second one. That's my intermediate phases here. And these into the third. Those are my 4 phases. Yes? So in this case, actually, these 3 clearly showed up after attempting to merge, which is not what we had with the binary segmentation to begin with. So what's nice about this method is that it gives you ability to guess. Does it always work nicely? No, because you might not have clear distinction between 3 different groups. We got 14 as a satisfactory result in a carbonate offshore Brazil, to the best of our ability to distinguish what's in the image. That was the 14 to go with. But it makes it easier in the cases where you don't know how many to go with to begin with. Okay? All right. So we're going to play with this in a little more difficult example next time and try to overcome some beam hardening with it.